I'm going to talk about differentiation, the ideas behind differentiation, what it means, and a few simple examples. Let's start off by looking at this sketch of a straight line. The vast majority of straight lines have equations of the form y equals mx plus c, where c is this point here, where the line cuts the y-axis, and m is the steepness of the line, the gradient of the line. So if, for example, I had an equation of the form y equals 2x plus 3, which could plausibly be the equation that goes with this straight line, then we would know that this line has a steepness of 2. It's got a gradient of 2, and it doesn't matter how far up or down we go along this line, in either direction, it will still have a gradient of 2. Lines don't change their gradients. They just carry on with the same gradient forever. Now, one way of thinking about differentiation is to say that it's about the gradient of a curve, the steepness of a curve. And the first thing that you may say, which would be a perfectly reasonable question, is what are you even talking about? How can a curve have a gradient? Well, let's have a look. Here we've got an example of a curve, and what would it mean to talk about the gradient of this curve? It sort of goes up, and then it goes down again, and then it goes up again. It's changing direction all the time. How can we get a gradient assigned to this? Well, because it does keep changing direction, we're only going to be able to talk about the gradient of that curve at a particular point. Let me show you with an example. Suppose we take that same curve, we look at a particular point on it, say this point here. What we can do is we can draw the straight line that just touches the curve at that point and nowhere else. This is called a tangent to the curve at that point. So this line we call a tangent. If you know anything about trigonometry, this is a different use of the word tangent from there. So in this case we're talking about the line that just touches the curve at that point. And what we mean by the steepness of the curve is the steepness of that line. It's the gradient of that line. So that means that the gradient at different points on the curve will be different. In fact, let's look at an example again. Here's the same curve, and I've now drawn a couple of straight lines that touch at different points. This one here gives you a very different straight line from this point here. In fact, this line is going upwards, it will have a positive gradient. This line's going downwards, it will have a negative gradient. So the gradient of a line at a particular point is what we mean by the gradient of the curve, and therefore the gradient of the curve will be different at different points. The gradient of the curve will not just be a number, it will be an expression, it will be a function that depends on where you are on the curve. Usually at this introductory level we look at it in terms of the x-coordinate of the point on the curve. Well, let's look at an example and see if we can actually work out how steep a particular curve is. And probably the simplest curve we can start off looking at is y equals x squared. So this is a little portion of y equals x squared for positive x values. And I want to work out the gradient of the line that touches this curve at a particular point. Well, I don't want to tie myself down to any particular point. Let's just take any point on the curve, which will have an x-coordinate of x, and the corresponding y-coordinate, because the curve has the equation y equals x squared. Well, if we've got an x-coordinate of x, the corresponding y-coordinate will be x squared. So here we are. Here's the point we've chosen on that curve. All we need to do now is draw the tangent to the curve at that point and work out how steep it is. Well, it turns out that's actually quite hard to do. So we're going to cheat a little bit. What we're going to do is choose another point a little bit further on from that one. Here we go. Here's a diagram with both of these points joined on. So I've started at this point we had before with an x-coordinate of x, and we've moved along a little distance called h. So we've got another point with an x-coordinate of x plus h. Well, again, because the curve is y equals x squared, that means the corresponding y-coordinate that goes with that point is x plus h, all squared. So this point has coordinates x plus h all squared. And what we're going to do is draw a straight line through those 2 points. And rather than work out the equation of the tangent at the point we started off with, the gradient of the tangent, we're going to work out the gradient of this straight line. Now I know that's not the gradient we actually want, but we'll worry about that later. So how do you work out the gradient of a straight line if you know 2 points? Well, I hope you all recall, you work out the distance you travel to get from the y coordinate of one to the other, in other words the difference between these two y coordinates, and divide it by the distance between these two x coordinates. We write this normally as delta y divided by delta x. This triangle is a Greek capital letter delta. Don't read this as two symbols, it's really one thing. It means the change in y divided by the change in x. So how do we work out the change in y? Well, if these were numbers it would be very easy. I mean, if that had a y coordinate of 9 and this had a y coordinate of 4, you would straight away tell me that the difference between them is 5. In fact, it's so easy it may not be obvious what you're doing, but what you're doing is subtracting the 4 from the 9, subtracting the lower coordinate from the upper one. So in this case that means that the upper coordinate, being x plus h all squared, we'll then have to subtract the lower coordinate, which is x squared. And what about the delta x? How far is it from here to here? Well, it's extremely easy to see that the distance from here to here is h. So that is the gradient of this straight line. It's not really much use to us looking like this. Let's see if we can simplify that. And the easiest way to start doing that is to expand this bracket on the top. If you expand x plus h all squared, you will get x squared plus 2x h plus h squared. And we've still got this negative x squared, subtracting x squared on the end there. That's all divided by h. That should make that clear, that really is still there. Now look, we've got an x squared at the beginning and a subtract x squared at the end, so they're going to cancel each other out, leaving us just with the 2xh and the h squared. And all of that is divided by an h. Well, because it's all divided by an h, it's still quite straightforward to simplify this a bit more. That will give us 2x plus h. That, therefore, is the gradient of this straight line. Now, as I said, that wasn't actually the straight line we wanted the gradient of. We wanted the one that just touched at the lower point. Well, what would happen if I make this h distance, the distance between these 2 points, smaller? In other words, if I slid this point closer back along the curve until it gets closer to the original point, well, the closer and closer we slide it, the closer and closer the straight line gets to the tangent at the point we're interested in. And we can't actually make it the same point, because then we'd only have 1 point and we couldn't work out a gradient. But we can see what happens as this h distance gets closer and closer. This gradient we've worked out gets closer to, and that's what this arrow means, it's getting closer to 2x as the h gets closer and closer to 0. So therefore it makes a lot of sense to say that the gradient of the tangent to the curve at that point is 2x. And indeed that is what we do. Now let's give it a piece of notation. In the same way that we said that the gradient of a line through 2 points was delta y divided by delta x, we're going to use a notation inspired by that, and it is dy dx. Best to say this as dy dx rather than dy over dx or dy divided by dx, because although we've taken our inspiration from a change in y divided by a change in x, there isn't any such thing called dy that we're dividing by a thing called dx. See this as a single piece of notation, dy dx. So we would say in this case dy dx is 2x. And as we said earlier, we would expect to get something which would be different for different points on the curve. I mean, one point on this curve would be 1, 1, for example. That's certainly on y equals x squared. And at that point, that means that the gradient of the curve, dy dx, at that point would be 2 times the x coordinate, which is 1. The gradient would be 2. But at another point on the same curve, so what's another point on the same curve? If we got an x coordinate of 2, we'd have a y coordinate of 4. That would mean that the steepness of the curve at that point would be 2 times the x coordinate, which is 2, would be 4. We get different answers depending where we are. And I hope you can see that the further you go along a y equals x squared curve, the gradient of the tangent will get larger and larger. Right, that is finding the gradient of y equals x squared. We call this process differentiation. In other words, if you start off with the equation y equals x squared, then we say that we differentiate it to work out dy dx. And in this case we've seen that dy dx is 2x. Let's do it with one more function. We don't even need pictures to do it. We can just follow the same method we had before. Let's take the next simplest function we can think of, which is y equals x cubed. Now if we start off with one point on that curve, which is x, and its corresponding y coordinate will be x cubed, and we'll pull the same trick. We'll move along just a little way to a point x plus h, and that's going to have a y coordinate of x plus h all cubed. Well, let's do the same thing. Let's work out what our delta y, the change in y between these points, divided by our delta x, the change in x between those points, will be. So, change in the y coordinate, how do we get from here to here? Well, as before, that will be x plus h all cubed, subtract x cubed. Along the x-axis, it's still h. I mean, the difference between x and x plus h is just h. As before, although this is the gradient of the line, it's not very useful to us. We need to expand out this bracket. Now, expanding out x plus h all cubed can take a little time if you do it in elementary ways. There is a shortcut to doing this using a thing called the binomial theorem. Doesn't matter if you don't know that yet. I'm just going to do this and tell you what the answer is. You can verify it yourself if you like. If we expand x plus h all cubed, we will get x cubed plus 3 lots of x squared h plus 3 lots of x h squared plus h cubed. Also, we've still got to take away this x cubed at the end, and we're still dividing by h. Well, similarly to last time, we've got an x cubed at the beginning and subtracting an x cubed at the end. Those two bits will go, leaving us just with the 3x squared h plus 3x h squared plus h cubed divided by h. And again, it's quite easy to simplify this expression. Divide through all of the terms on the numerator by the h in the denominator. That will give us 3x squared plus 3xh plus h squared. That would be the gradient of the line that passes through the 2 points that I gave. But as before, we didn't actually want that gradient. We wanted the gradient which just touched at one of the points, and we can get that by letting the h again get closer and closer to 0. Slide that second point down till it gets closer to the first point. So what happens to this expression? What does it get closer to as h gets closer to 0? Well, as h gets closer to 0, this bit will go off to 0. And so will this bit. But that bit hasn't got any h's in it, so it will still stay there. So we'll get closer and closer to 3x squared as h gets closer to 0. So what have we found? Using the language that we used earlier, we have found that if you start off with the curve y is x cubed, then it follows that when you differentiate, when you work out what dy dx is, you get the answer 3x squared. If we put that together with the one that we did earlier on we found that when y was x squared, then when we differentiate to get dy dx, in that case we got 2x. Now you may think that you can see a pattern here, and you may be correct. So let's go on to the next video to actually look at examples of this, see if we can extract the pattern and use it in general. One final point that is worth saying is that in most introductory courses you will not need to have to do this process for yourself. This is called differentiation from first principles. What we're really doing is making sure you understand what the process means, so you understand what you're doing when you're differentiating. But in practice, we're going to take a rule that we can work out from these examples and a couple of other examples, and then just use that in practice from now on.